We're going to sketch this function and calculate some more Riemann sums, except this time this function is going to cross right through the x-axis in the middle of the given interval. So 2 minus 2x squared looks like a parabola that opens downwards. At x equals 0, the value of the function is 2. At x equals 1, the value of the function is 0. At x equals 2, you can find that the value of the function is negative 6 by plugging x equals 2 in right here. If we plug x equals 3 into this function, we get a y value of negative 16. And if we plug x equals 4 into this function, we get a y value of negative 30. So our function looks something like this. Fortunately, our n value for these Riemann sums is going to be 4, so that splits up our interval very nicely. Let's take a look at a left Riemann sum first. We have 4 subintervals, and we're going to look at the leftmost point on each of these 4 subintervals to determine the height of each one of these rectangles. So in our subinterval from 0 to 1, the height of this rectangle looks like it's going to be at 2. For the subinterval between 1 and 2, we use the value of the function at x equals 1 to determine the height of our rectangle, and that turns out to just be 0. For our subinterval between x equals 2 and x equals 3, we have this rectangle. And for our subinterval between x equals 3 and x equals 4, our left Riemann sum is going to include this rectangle right here. Adding the areas of those 4 rectangles up gives us L4. Now this first rectangle over here, you'll notice has a height of 2 and a width of 1. This second rectangle has a height of 0 and a width of 1. Our third rectangle is below the x-axis, so we're going to count this as a negative area. Its height is then going to be negative 6 and its width is 1. And this last rectangle here has a height of negative 16 and a width of 1. If you add all of those numbers together, you get a net area of negative 20 for your L4. This is a good time to hit pause on your browser because I'm going to erase these rectangles to make room for our right Riemann sum. For our right Riemann sum, we're going to take the rightmost point in each one of these 4 subintervals, and that's going to determine the height of each one of our rectangles. So with our right Riemann sum, our first rectangle has a height of 0 and a width of 1. Our second rectangle is below the x-axis, so we're going to count it as negative. It has a height of negative 6 and a width of 1. Our third rectangle has a height of negative 16 and a width of 1. And our fourth rectangle has a height of negative 30 and a width of 1. Adding all of the areas of those 4 rectangles up gives us a net area of negative 42. Again, this would be a good time to hit pause on the video if you want to take a look at these rectangles, because I'm going to erase them one more time to make some room for our midpoint Riemann sum. A midpoint Riemann sum takes the midpoint of each one of these 4 subintervals, looks at the value of the function at that midpoint, and that determines the height of the rectangle. And it looks like we're going to need to do some calculations to find the heights of each of these rectangles. The height of this first rectangle is given by the value of the function at an x value of 1/2. That's 1/2 of the way between x equals 0 and x equals 1. Doing that calculation is going to give us a height of that first rectangle of 3/2. So down here we're going to have a height of our first rectangle of 3/2 and a width, of course, of 1. That rectangle is above the x-axis, so we're going to call it positive. The height of our second rectangle is going to be given by the function value when our x value is halfway between 1 and 2. That's an x value of 3/2. So we'll plug x equals 3/2 into our original function. I'm getting a height of negative 5/2 from that function. So that means that the area of this rectangle in our Riemann sum is negative 5/2, that's its height, times a width of 1. The height of our next rectangle is given by the value of the function when x is halfway between 2 and 3. Halfway between 2 and 3 is 5/2, so I'm going to plug x equals 5/2 into this function. That's giving me a value of negative 21/2, meaning that the height of this rectangle is negative 21/2, multiplied by a width of 1, gives us that area of that rectangle. And lastly, to find the height of this final rectangle at an x value halfway between x equals 3 and x equals 4. That would be an x value of 7/2. I'm getting that value is negative 45/2. So the height of this particular rectangle is negative 45/2. We multiply that by a width of 1 to get the area of that rectangle. And now we need to simplify this expression. I'm getting a value of negative 34 as the approximate area between this curve and the x-axis using a midpoint Riemann sum. Now one more time, hit pause on a video right now if you want to take a closer look at this, because I'm going to erase it. Because I want to point out that the area that we're approximating with all of these Riemann sums is the entire area between the given function and the x-axis on the interval x equals 0 to x equals 4. Whatever area is above the x-axis we think of as positive, and whatever area is below the x-axis we think of as negative. So given this graph, we can see that positive contributions are given to this net area on the interval 0 to 1. And then we get negative areas for this particular function on the interval from 1 to 4. And I think that that's going to do it for that problem. I hope that this helps you out with left, right, and midpoint Riemann sums. Hopefully this wasn't too tedious. We'll talk a little bit more about areas under curves in the next video. I'll see you there.